The next talk is a joint talk. I'm delighted to introduce Professor Alexandre Borovik from Manchester University and Professor Şükrü Yalçınkaya from Estonia University. The title of the talk is Monte-Carlo Methods and Black Box Algebras.
Thank you very much for giving us opportunity to talk at this remarkable conference. Can you hear me, first of all?
Yes, we hear you.
Yes, okay, fine. Also, do you see my screen?
No, not yet.
I clicked share the screen without much effect. Let me see what is happening with it. Share a screen. Yes, which screen? Yes, this screen. Share. Now?
Yeah, now we see your presentation. Yeah, it's
Okay,
good.
fine. In this case, I can start the presentation. First of all, I wish to say that I heard in the remarkable previous talk that Jordan homomorphisms are everywhere. I wish to start my talk with saying that Monte Carlo methods are everywhere, but mostly in applied mathematics. And let me see that. Okay, one more thing I have to do. I have to do a big screen and oh yes. They are everywhere in mathematics, but mostly in applied mathematics. Widely used. They were invented in by Stanislav Ulam in 1946 in Los Alamos National Laboratory for the purposes of calculations of neutral diffusion paths in the hydrogen bomb. But now are used in a wide range of applications. Really great mathematicians were working on the initial development of the method, like John von Neumann, for example, or Nick Metropolis. But the very birth, the conception of, or even conception of the method was done by Ulam in strictly algebraic context. He was ill and played solitaire, some card game with it, and decided to think about obvious question: what is the probability that a hand laid with 52 cards will come successfully at the end? He realized that combinatorial approach is useless, but already was thinking that perhaps just computer experiment on 100 layouts will give a good estimate of probability. On return to work, he applied this to trajectories of neutrons in a hydrogen bomb. But the very first use of Monte Carlo was in group theory. In the 1980s, the Monte Carlo method in groups was used and promoted by Laszlo Babaye in his work on graph isomorphism problem. Babaye discovered that finite simple groups can be identified by statistics of orders of random elements. You simply collect how many, on average, elements of order 2, 3, 5, and blah, blah. But with one interesting exception. Between orthogonal groups in odd dimension and symplectic groups, the simple versions of a finite field, this method does not work because statistics of elements in them are practically identical and cannot be identified in polynomial time. It was solved by 2001 this issue by Christine Alzheimer by very deep penetration in the structure of the group. However, in this penetration, every step was a Monte-Carlo method, again, finding something by testing. So, black box algebra, as Şükrü and I understand it, is answering specific questions about, and maybe even recovering the structure of an algebraic object, say group ring, projective plane, Boolean algebra, Hating algebra in mathematical logic, perhaps unknown to us, by manipulating with its random elements. Some reasonable concept of randomness is needed for that, like with the help of a measure on compact Lie groups, or genericity in model theory also gives good approach to that. The key point is estimation of probability of an error. Error present intrinsically in this approach, but by repeating tests, you can make it exponentially small, beyond any kind of statistical ensembles of statistical physics, beyond anything which exists in universe. And we treat that as a black box. Definitions will follow in a few minutes. My task here is to demonstrate that even in problems which we do in computation in finite groups, this new universe opens up when exactly the same methods can work being usable in fantastic variety of applications. Well, I will consider only one mental experiment. Imagine a communication between Şükrü and I, denoted by Y, and Mother Nature. Mother Nature knows the structure of the universe in the form of connected Lie group. We know that it is a Lie group, simple Lie group, connected simple Lie group, and suspect, without having any evidence, that this is our familiar group of rotations of Euclidean three-dimensional space, SO3. We may ask Mother Nature to produce random elements from X and manipulate with them on our request. And this request is remarkable. We ask to Mother Nature do something and assign name to the result. We assign a name. We do not see any actual computations, any actual elements. These operations are just multiplications, inversion, group theory, and, which matters in quantum mechanics, extraction of roots. Spin is the square root of rotation. And remarkably, after finitely many questions and answers, we can confirm that this is indeed the group as we suspected, with probability of error, which beyond could be made arbitrarily small. More interestingly, that we construct in the process a Euclidean space, three-dimensional, and can do various things in it. For example, construct an icosahedron, which is the apex of Euclid's elements. And this actually matters, because this structure appears in calculations in matrix groups over finite fields. And I stop my sharing and give the chance to Şükrü to continue this talk.
Hello. Can you hear me? And can you see these slides?
Yes, yes.
Okay, great. Let me continue a little bit of details of black box algebra. Sorry. First of all, I'd like to thank the organizers for this wonderful conference and allowing us to share our results. And yeah, so I want to start in a very basic setup in the matrix group problems. So for example, when we are given finitely many matrices, invertible matrices, n by n, defined over a finite field, the natural question is that what is this group? What is the order of this group, for example? And another more ambitious project is to find the composition factors of the group, construct the composition factors of the group in an efficient time, of course, which means the probabilistic time polynomial in n log q as it appears in this setup to be an input length of the group. And if one can construct the composition factors, the next question would be, what are these composition factors, for example? Can we decide for example, one of these groups are PSLN or something like this, any simple group. And much more reasonable ones are obviously matrix groups in this setup. So can we decide whether the groups are SLN or SPN or any other matrix group? And if you decide, and can you construct an isomorphism between this given matrices and the known group, which is given naturally as SLN can be given naturally as an m by n matrices of determinant 1. And the problem in here is that the order of the group can get extremely large when n and q gets larger and larger. And therefore, the deterministic approaches cannot be used in this case. So they are not actually even discussed in the setup. So the recognition of the Chevalier groups is actually one of the main areas in this setup. And the most difficult part of the recognition of a Chevalier group is to deal with the groups SL2. Okay, and to deal with this SL2, one needs to find a non-trivial unipotent element inside the group to construct two-way isomorphisms between SL2 and the given group. Okay, and this problem is pretty difficult and remained open for many years. And the reason for that is unipotent elements are very rare in these groups when the underlying field is very large. Indeed, the probability of hitting a unipotent element inside SL2 or any other Chevalier group is like 1 over Q, where Q is the size of the underlying field. So when Q is big, it is almost impossible to hit a unipotent element at random. Therefore, we see this X as a compact Lie group. Okay, and we have an answer to this problem. Very efficient algorithm. We have a very efficient algorithm solving this problem in the case of SL2 when P is odd. We tested our algorithm in GAP. This is the package used for group theoretic problems and some other problems as well in computational group theory. It's called Groups, Algorithms, and Programming. And I can proudly say that this our algorithm we tested our algorithm over these primes. Like this is a 30-digit prime. And funny facts about this group, for example, that the number of elements in this group is much more than the number of electrons in the observable universe. And the probability of hitting an important element is just not possible. So the way, well, when we solved this problem, we actually did not use any specific properties or how this X is given to us. Like it's not a matrix. We did not use any specific properties of matrices or whatever. So we basically focused on only the structures of this X, and this brings us to the terminology black box groups. Okay, black box group is a black box together with a group where black box encrypts the elements of the group as 0, 1 strings of uniform length. And we want this black box to compute multiplications in the group, taking inverses and comparing whether the strings representing the same element or not. And obviously, we want to have an access to uniformly distributed random elements in this group so that we can work inside of this group. As you can see, this is a very general setup and very abstract setup, and we can use this idea basically to black box almost anything, any algebraic structure by just allowing this black box to compute any algebraic operations inside the algebraic structure. Okay. And this is the setup. This is a slight generalized setup introduced by Baba and Zezemered in 1984. And we want this generalization in a sense that when we solve this unipotent element problem, we needed to construct more black box structures inside a given black box structure. And this BB1 and BB3 is just the ones I was talking about in the previous slide. And unfortunately, using these three axioms, one can do almost nothing. I mean, it's almost impossible to get the structure of the given group by just using this BB1 to BB3. One needs to have some more axioms, and over the years we came to this axiom C, which we call it, which is actually the extracting a square roots of a given element if they exist in the central part of its centralizer. This is just a discussion. This is just the analog of the discussion of the with the modern nature in the previous part. So as you see, we can by using this BB1, BB3, we can black box almost anything, even projective planes. In the case of projective planes, we needed a black box to compute, give us a uniformly distributed random points, of course. But given 2 points, we want this black box to compute lines and finding the intersection of the lines and etc. Okay. An example of a black box, for example, in gap, if you can implement a group inside a gap, this is a perfect example of a black box group. As the computer does the computations, we have no idea what's going on inside, and we just have the results provided us. And also, the black box algebra, as we introduced here, we want our black box to compute the algebraic operations. So it preserves the algebraic operations. So it's actually it can be seen actually a structural theory behind the homomorphic encryption here. And in the case of 80s, black box fields, for example, are one of the main research areas in cryptography and used heavily by cryptographers and computer scientists. Okay, let me talk little bit about the black box field because it gives us the natural difficulty in the isomorphisms when we want to provide isomorphism between a given black box group and its natural copy. And the isomorphism of the problem in the case of two black box fields having encrypting the same finite field, the isomorphism between them is polynomial time equivalent to the isomorphism between the prime fields. So any isomorphism between the prime fields can be extended efficiently to larger fields, to the extensions. This was the combinations of results, which was first provided by Lenstra Jr. in 1991, and then more recently by Maurer and Robb in the black box setting. An obstacle here is the isomorphism problem on the black box fields, assuming that we have a prime field black box field K0 encrypting a prime field FP, P prime. We always have an isomorphism from FP into K0 by just sending the element 1 in FP to the element 1 in the black box 1. And any element inside FP like M can be, the image of this M can be computed efficiently by doubling and add method inside K0. However, the reverse isomorphism involves for example, constructing an image of an arbitrary element in K0, one needs to find which powers of this element raised to 1. So this is precisely the discrete logarithm problem. And this is a very difficult problem, and it's an open problem. And it is actually the base of all the cryptographic applications. However, obviously, for small primes P, as in the previous slide shows us, for small primes, black box fields of order P to the n can be effectively isomorphic to the P to the n. So, the crucial part here is to work with the big primes. Okay, like in the case where in the one of the beginning slides, earlier slides, I had this 30-digit prime, for example. So this is a much more difficult problem than the small prime numbers. Okay, to remove this difficulty and provide much better or much more focused based on the structure of the groups and even an algebraic structure, we introduce this structural proxy, which we call it. Suppose that we are given a black box structure X encrypting A of F. For example, A is here, can be thought of these Chevrolet functors like B and or E6 or any other Chevrolet types. F here is the field. The structural proxy of this algebraic structure is to construct a black box field encrypting the underlying field, and the two-way isomorphisms between the functor realized over the black box field and given the black box structure. Okay. Sorry. In the case of SL2, we have a solution to this problem, exactly as in this setup. So we have a structural proxy for SL2. Although we cannot have two-way isomorphism between SL2F, where F is a nicely given field, but we have this two-way isomorphism between a black box group and the SL2 realized over this black box field. The ingredients of this algorithm is based on actually constructing even projective, constructing a Lobachevsky plane actually for the group PGL2. So it is easy when you start with SL2. It is easy to work with PSL2 by just thinking everything modulo scalars, the central involution. And then we manipulate this black box PSL to construct a diagonal automorphism so that we can assemble this diagonal automorphism to this PSL2 and get this PGL2. And with this PGL2, we can construct this Lobachevsky plane, underlying projective plane. And as soon as we have this projective plane, we have an access to black box field, underlying field. And coordinatizing this projective plane, we have these two-way isomorphisms. And yeah, this is although it looks it covers all the slides, but looks very innocent. It involves a fantastic number of beautiful constructions inside of it. And Borovik and myself are working on, obviously, to move further and construct this structural proxy for all Chevrolet groups. And if I have time, I can actually run an experiment on GAP, how fast and how beautiful the construction of a unipotent element inside the SO3 can be. I can show it to you as well.
Yes, please.
Okay, great. In this case, I need to share another screen. Share this. Can you see this GAP screen?
Yes.
Oh, brilliant. Okay. So can I type on it? Brilliant. Okay, so for example, 997 is a prime. It's not a very big prime like 30-digit prime as in the beginning, but obviously I don't have that many minutes. So 997 is okay for the practical purposes. So for simplicity, I want to introduce this SO3 to input this group. GAP knows the generator, so I ask for it. And instead of using the square root function ability to extract square roots, I just assume the actually exponent, a global exponent. And 3 by 3 matrices over this file, you just immediately find the order of GLN, GL3997 as an exponent and work with this. So even though I put order here, it is a natural assumption, okay? So I input this, ask for the function name is unipoly, and actually it exactly does whatever I said in the previous slide. So yeah, it constructs, first of all, the projective plane and constructs the black box field underneath, and then solve some problem about the quadratic equations, because the unipotent element lies on the quadrics inside the projective plane. So I can give you order of this group, order of this element, and this is the, I believe, third entry in this output. I guess it is 997, right? Yeah. Yeah. Bigger primes can be used as well. For example, like, let me this time provide small prime, big power, and do the same. Again, it does the same thing, construct the projective plane, construct the field, and try to solve some problems about this. Well, it doesn't have a print screen in this case, but let's check whether it is of order 5. It should be 5, yeah. Well, thank you.
Thank you.